A process is basically a program in execution. The execution of a process must progress in a sequential fashion. The status of the current activity of a process is represented by the value of program counter and the contents of the process registers. The memory layout of a process is typically divided into multiple sections. These sections include text section contains the executable code. This includes the current activity represented by the value of program counter and the contents of the process register. Data section. This section contains the global and the static variables. Heap section. This is dynamically allocated memory to process during its runtime. Stack section. The process stack contains the temporary data such as method or function parameters, return address, and the local variables. The process is not as same as program code, but a lot more than it. A process is an active entity as opposed to the program, which is considered to be a passive entity. A program becomes a process when an executable file is loaded into the memory. We can either double-click on the GUI icon of the executable file or type in the name of executable file in the command line. Although two processes may be associated with the same program, they are considered to be two separate execution sequences. For example, if you open multiple web browsers, each web browser is a process. Their text sections are maybe equivalent, but the data heap and the stack sections are different. This figure illustrates the layout of a C program in memory, highlighting how the different sections of process related to an actual C program. This figure is similar to the general concept of a process in memory, with a few differences. In the data section, it is divided into two different sections. First is initialized data. Integer y equals 15, that's initialized data. The second section of the data section is for uninitialized data. Integer x, x is uninitialized. Both x and y are global variables. The heap section contains dynamically allocated memory. The stack section contains local variables. On top, a separate section is provided for argc, argv parameters passed to the main function. The GNU size command can be used to determine the size in bytes of these sections. So you just need to type in the command size, S-I-Z-E, and the name of the executable file. As a process executes, it changes state. The state of a process is defined in part by the current activities by that process. A process may be in one of the following states. New, the process is being created. Running, the instructions are being executed. Waiting, the process is waiting for some event to occur. Ready, the process is waiting to be assigned to a processor. Terminated, the process is finished execution. This state diagram shows only one process can be running on any processor core at one instant. So many processes may be in the ready and the waiting state. Process control block, PCB. A process control block is a data structure maintained by the operating system for every process. The PCB is identified by integer process ID, PID. A PCB keeps all the information needed to keep track of a process. Process state, the current state of the process. For example, whether it is ready, running, waiting, or whatever. Program counter. Program counter is a pointer to the address of next instruction to be executed for this process. CPU register. Various registers where process need to be stored for execution for running state. CPU schedule information. Process priority and the other schedule information which is required to schedule the process. Memory management information. This includes the information of page table, memory limits, segment table depending on memory used by the operating system. Accounting information. This includes the amount of CPU used for process execution, time limits, execution ID, etc. I/O status information. This includes a list of I/O devices allocated to the process. The PCB is maintained for a process throughout its lifetime and is deleted once the process terminates. Most modern operating systems have extended the process concept to allow a process to have multiple threads of execution and thus to perform more than one task at a time. This feature especially benefits on multi-core systems where multiple threads can run in parallel. On systems that support threads, the PCB is expanded to include information for each thread. This is one example of the process control block, PCB, in the Linux operating system. And we can see it maintains the information on state of the process, scheduling information, process parent, process children, list of open files, address space. The state of process is represented by the double-linked list of task and the score struct. And if we want to assign a new state, we can say current pointer state, then we assign the new state to the current state. The process scheduling is the activity of the process manager that handles the removal of running process from the CPU and the selection of another process on the basis of a particular strategy. Process scheduling is an essential part of a multi-programming operating systems. Such operating systems allow more than one process to be loaded into the executable memory at a time, and the loaded process share the CPU using time multiplexing. The operating system maintains all PBC, process control block, in the process scheduling queues. The OS maintains a separate queue for each of the process states, and the PCBs of all processes in the same execution state are placed in the same queue. When the state of a process is changed, the PCB is unlinked from its current queue and moved to its new state queue. The operating system maintains the following import process scheduling queues. The ready queues is set all processes residing in main memory, ready and waiting to execute. Wait queues, set of process waiting for all event, for example, input, output. So process migrates among the various queues. As a process enters the system, they are put into a ready queue where they are ready and waiting to execute on a CPU's core. This queue is generally stored as a linked list. A ready queue header contains pointer to the first PCB in the list, and each PCB includes a pointer field that points to the next PCB in the ready queue. The system also includes other queues. When the process is allocated a CPU core, it executes for a while and eventually terminates or is interrupted or waits for the occurrence of a particular event, such as the completion of an I/O request. Suppose the process makes an I/O request to a device such as a disk. Since devices run significantly slower than processors, the process will have to wait for the I/O to become available. The process that are waiting for a certain event to occur, such as completion of I/O, are placed in a wait queue. This figure shows a queuing diagram. The arrow indicates the flow of process in the system. A new process is initially put in the ready queue. It waits there until it is selected for execution, or we call it dispatched. Once the process is allocated a CPU core and is executing, one of several events could occur. The process could issue an I/O request and then be placed in an I/O wait queue. The process could create a new child process and then be placed in a wait queue while it waits the child's termination. The process could be removed forcefully by the core as a result of an interrupt or having its time slice expire and be put back in the ready queue. In the first two cases, the process eventually switched from the waiting state to the ready state is then put back in the ready queue. A process continues this circle until it terminates, at which time it is removed from all queues and has its PCB and the resource deallocated. A context switch is the mechanism to store and restore the state or context of a CPU in process control block, so that a process execution can be resumed from the same point at a later time. Using this technique, a context switcher enables multiple processes to share a single CPU. Context switching is an essential part of a multitasking operating system features. When the scheduler switches the CPU from executing one process to execute another, the state from the current running process is stored into the process control block. After it, the state of the process to run text is loaded from its own PCB and used to set the PC, register, etc. At that point, the second process can start executing. In this figure, we can see we have a process 0 and a process 1. At the beginning, process 0 is executing. Then it is interrupted or has a system call. So it saves the state into the PCB of process 0. Then process 1, it was idle. That time, it loaded state from P1's PCB. So P1 start to executing. And the P0 become idle. And when after P1 has interrupt or system call, it saves state into PCBs of P1. Then the P1 become idle and the P0 can execute. So it reloads state from PCB 0. When a context switch occurs, the kernel saves the context of the old process in its PCB and loads the saved context of the new process scheduled to run. Context switch time is pure overhead because the system does no useful work while switching. Switching speed varies from machine to machine depending on the memory speed, the number of registers that must be copied, and the existing of special instructions. A typical speed is several microseconds. Context switch times are highly dependent on hardware support. For instance, some processors provide multiple sets of registers. A context switch here simply requires changing the pointer to the current register set. Multiple contexts can be loaded at once. Nowadays, mobile systems allow a single foreground application to run concurrently with multiple background applications. On mobile device, the foreground application is the application currently open and appearing on the display. The background application remains in the memory but doesn't occupy the display screen. Android has supported multitasking and doesn't place constraints on the types of applications that can run in the background. If an application requires processing while in the background, the application must use a service, a separate application component that runs on behalf of the background process. Consider a streaming audio application. If the application moves to the background, the service continues to send audio data to the audio device driver on behalf of the background application. In fact, the service will continue to run even if the background application is suspended. Services don't have a user interface and have a small memory footprint, thus providing an efficient technique for multitasking in a mobile environment. The processes in most systems can execute concurrently, and they may be created and deleted dynamically. Thus, this system must provide a mechanism for process creation and termination. During the course of execution, a process may create several new processes. As mentioned earlier, the creating process is called a parent process, and the new process are called the children of that process. Each of these new processes may in turn create other processes, forming a tree of process. Most operating systems, including Unix, Linux, and Windows, identify process according to a unique process identifier, PID, which is typically an integer number. The PID provides a unique value for each process in the system, and it can be used as index to access various attributes of a process within the kernel. The parent process and the children process can share all resources, or the children only share a subset of parents' resources, or parent and the children don't share any resource. For the execution, the parent process and the children process can execute concurrently, or the parent must wait until children terminate. This figure illustrates a typical process tree for a Linux operating system. The system MD, which always has a PID of 1, serves as the root parent process for all user processes, and is the first user process created when the system boots. Once the system has booted, the system D process creates process which provide additional service. For example, the login D process is responsible for managing clients that directly log on to the system. In this example, a client has logged on and is using the bash shell, which has been assigned PID A416. Using the bash command line interface, the user has created process PS as well as the vim editor. System D also created SSHD. The SSHD process is responsible for managing clients that connect to the system by using SSH, which is short for Secure Share. There are two address space possibilities for the new process. The child process is a duplicate of the parent process. It has the same program and the data as the parent. Or the child process has a new program loaded into it. In Unix, we have seen each process is identified by its process identifier, which is a unique integer, PID. A new process is created by fork system call. The new process consists a copy of the address space of the original process. This mechanism allows the parent process to communicate easily with its child process. Both processes, the parent and the child, continue execution at the instruction after the fork system call, with one difference. The return code for the fork is 0 for the new child process, whereas the non-zero process identifier of the child is returned to the parent. After a fork system call, one of the two processes typically use XC system call to replace the process memory space with a new program. The ch3 exec system call loads the binary file into memory and starts its execution. The two processes, the parent and the children, are able to communicate and then go their separate ways. The parent can then create more children, or if it has nothing else to do while the children runs, it can issue a wait system call to move itself off the ready queue until the termination of the child. Because the call to ch3 overlays the process address space with a new program, ch3 didn't return control unless an error occurs. In this figure, we can see we have a program. The parent called PID equal fork. So after this fork, the parent PID is greater than 0, while the child PID is equal to 0. And in this example, the parent will wait, so it issue a wait system call. During that, the child will execute, so it issues xc call, and when it terminates, it issues exit system call. Then once the child is terminated, the parent can resume. This is an example of a C program. PID equal fork, so it will create a new process. If the PID of newly created process is less than 0, that means the error happened. If PID equal 0, if PID is 0, it identifies child process. The child has the command execlp. So execlp is the same as exec. In this example, the child process overlays its address space with the Unix command /bin/ls. It used to get a directory listing using the execlp system call. And if PID is not equal to 0, that's a parent process. The parent waits for the child process to complete with the wait system call. When the child process completes, so they issue an exit system call, the parent process resumes from the call to wait. So in this example, it will continue to have a printf command, so display the message child complete. So in this example, the parent and the child process are able to communicate and they go their separate ways. If the child doesn't invoke exec or execlp, instead it continues to execute as a copy of the parent process. In this scenario, the parent and the child are concurrently process running the same code instructions. Because the child is a copy of the parent, each process has its own copy of any data. Fork function is used in Unix. In Windows, we use create process function. It is similar as fork function in Unix. Let's see an example for creating a separate process via Windows API. First, we have a startup info and the process underscore information. Those two parameters are needed for create process function. So startup info specify many properties of the new process, such as window size, appearance, and the handles to standard input and output file. The process underscore information structure contains a handle and identifier to the newly created process and its thread. And we use zero memory function to allocate memory for each of these structures before processing with create process function. The first two parameters passed to create process function are the application name and the command line parameters. If the application is null, as in this case, the command line parameter specify the application to load. In this example, we are loading the Microsoft Windows MS Paint.exe application. Beyond these two initial parameters, we use the default parameters for inheriting process and the thread handles, as well as specifying there will be no creation flags. We also use the parent's existing environment block and the starting directory. Last, we provided two pointers to startup info and the process underscore information structure created at the beginning of the program. In previous Unix program, the parent process waits for the child to complete by invoking the wait system call. The equivalent of this in Windows is wait for single object system call, which is passed a handle of the child process, pi.h process, and waits for the process to complete. Once the child process exits, control returns from the wait for single object function in the parent process. Then the parent will execute the next command, which is a printf child complete. So child complete message will be printed. After the process has completed the execution of its last instruction, it is terminated. The resources held by a process are released after it is terminated. So a child process can be terminated by its parent process if its task is no longer relevant. The child process sends its status information to the parent process before it terminates. Also, when a parent process is terminated, its child process are terminated as well, as the child process cannot run if the parent process are terminated. The parent may also terminate the execution of the child process using the abort system call. Some reasons for doing so is child has exceeded allocated resources. The task assigned to child is no longer required. The parent is exiting, and the operating system doesn't allow a child to continue if its parent terminates. Some operating systems don't allow a child to exist if its parent has terminated. In such system, if a process terminates, then all its children must also be terminated. This phenomenon, referred as cascading termination, is normally initiated by the operating system. The parent process may wait for termination of a child process by using the wait system call. The call returns status information and the PID of the terminated child process. So PID equal wait, then the parameter is the address of status variable. If the parent doesn't call wait system call, so the child will become a zombie process. All processes transition to this state when they terminate, but generally they exist as zombies only brief. Once the parent calls wait, the process identifier of the zombie process and its entries in the process table are released. If a parent didn't invoke wait and just terminated, then leaving its child process as orphans. Traditional Unix system address this problem by assigning the init process as the new parent to orphan process. As before, we see the init serves at the root of the process architecture in Unix system. The init process periodically invoke wait system call, thereby allowing the exit status of any orphan process to be collected and releasing the orphan process identifier and process table entry. Mobile system has limited memory. Mobile operating system may have to terminate existing process to reclaim limited system resources. Android has identified an importance hierarchy of process, and when the system must terminate a process to make resources available for a new or more important process, it terminates process in order of increasing importance. So the most important is the foreground process. It is the current process visible on the screen. Then the second one is a visible process, a process that is not directly visible on the foreground, but is performing an activities that the foreground process is referring to. Third one is the service process, a process that is similar to a background process, but is performing an activity that is apparent to the user. The fourth one is background process, a process that may be performing an activity but is not apparent to the user. The least important is the empty process, a process that holds no active components associated with any application. Inter-process communication. A process is independent if it doesn't have shared data with any other process executing in the system. A process is cooperating if it can affect or be affected by other processes in the system. There are several reasons for providing an environment that allows process cooperation. The process can have information sharing, computation speed up, modularity, and convenience. Cooperating process require an inter-process communication mechanism, IPC, that will allow them to exchange data, send data, and receive data from each other. There are two types fundamental models of inter-process communication: shared memory and the message passing. In the shared memory model, a region of memory that is shared by the cooperating process is established. Process can then exchange information by reading and writing data to the shared region. In message passing model, communications take place by means of message exchange between the cooperating process. So both of the models just mentioned are common in operating systems, and many systems implement both. Old web browsers run as a single process, so there will be problems if one tab fails. All other tabs, all other web browsers can also crash. Google Chrome web browser was designed to address this issue by using a multi-process architecture. Chrome identified 3 different types of process: browser, renders, and plugin. The browser process is responsible for managing the user interface as well as disk and the network I/O. A new browser process is created when Chrome is started. Only one browser process is created. For the render process contain logic for rendering web pages. Thus, they contain the logic for handling HTML, JavaScript, image, and so on. As a general rule, a new render process is created for each website opened in a new tab, and so several render processes may be active at the same time. A plugin process is created for each type of plugin, such as Flash or the QuickTime in use. Adobe no longer supports Flash plugin because it's not safe. Extensions are considered trusted when they are built by a developer who follows the Chrome Web Store developer program policies. The advantage of the multi-process approach is that websites run in isolations from one another. If one website crashes, only its render process is affected. All other processes remain unharmed. Furthermore, render process run in a sandbox, which means the access to disk and the network I/O is restricted, minimizing the effects of any security exploit. The concept of cooperating process is similar as a producer-consumer problem. A producer process produces information that is consumed by a consumer process. One solution to the producer-consumer problem is to use shared memory. There are 2 types of buffers can be used: The unbounded buffer places no practical limit on the size of the buffer. The consumer may have to wait for new items, but the producer can always produce new items. The bounded buffer assumes a fixed buffer size. In this case, the consumer must wait if the buffer is empty, and the producer must wait if the buffer is full. The following variables reside in a region of memory shared by the producer and the consumer process. The shared buffer is implemented as a circular array with two logical pointers, in and out. The variable in points to the next free position in the buffer. The out points to the first full position in the buffer. The buffer is empty when in equal to out. The buffer is full when in plus 1 modularized buffer size equals out. In this type of implementation, the buffer can only use buffer underscore size minus 1 elements. The code for the producer process is shown on the left, and the code for the consumer process is shown on the right. The producer process has a local variable, next underscore produced, in which the new item to be produced is stored. The consumer process has a local variable, next underscore consumed, in which the item to be consumed is stored. Let's take a look at the producer process. There's an outer while loop. That means it's a producer-consumer situation. It's keep running. The inside, we also have a while. Also pay attention. For this while statement, we have a semicolon immediately after this while loop. So when the condition in plus 1 module buffer size equals out, if this is true, the producer process will do nothing because the buffer is full. When this is not true, that means the buffer is not totally full. So it will move to the next command, which is buffer in equal next produced. So it will put the item next produced in buffer in. Then it will recalculate the in, which is in plus 1 modularized buffer size. For example, at the beginning, in and out both equal 0. So if we go into this inner while, so in plus 1, which is 1, modularized buffer size, let's say buffer size equal 10. So 1 module 10 equal 1. So it's not equal to 0. Out is 0 that time. So it says, okay, I can produce. So the next produce, the item will be stored in buffer 0 position. And then the in plus 1, which is 1, modularized buffer size, which is 10. So in plus 1 module buffer size equals to 1. So 1 will be assigned to in. So in updated to be 1. Let's take a look of a consumer process. Also has an outer while loop, so it's a producer-consumer process. Then inside we have an inner while loop. While in equals out and a semicolon. This semicolon is important. So when in equals out, for example, both in and out are 0. That means the buffer is empty. So it does nothing. So it just keep looping without doing anything, right? Because the while is an empty loop doing nothing. While this in is not equal to out, that means there's some item in the buffer. So the consumer can move on. So we assign the buffer out to the next underscore consumed. So buffer out, we have the example, the out equals 0, which is the first item in the buffer, then assigned to next underscore consumed. Then we also update the new out, the out plus 1, which equals to 1, modulus 10 becomes 1. So the out is now equal to 1. So right now, both in and the out equals 1. That means the buffer is empty, right? Because the producer just produced one item and the consumer just consumed one item. So the buffer is empty. So in and out both equal to 1. So the consumer will not consume anything, right? Because in the while loop, in equals out. So it will go on like this. The consumer will wait until the producer produce one item. Suppose when in equals 8, next underscore produce is assigned to buffer 8. So in plus 1, which is 9, module 10, which is 9. So in update to 9, right? That time, when in update to 9, then it's keep looping the outside the while loop. So we'll execute this while loop, the inner while loop. In plus 1 modulus the 10, right? In plus 1 is 10 modulus buffer size, which is 10. Actually, so this becomes 0. And suppose the out is 0 too. That means the consumer doesn't consume anything, right? So this becomes true. Then this while loop will do nothing, keep running. So 9th position is actually is empty, is not put any item, right? So the items occupy from 0 to index 8 of the buffer. So buffer 0 to index 8, it actually has 9 elements, not 10 elements. So in this solution, it can only use the buffer size minus 1 elements. In shared memory, a producer can produce one item while the consumer is consuming another item. The producer and the consumer must be synchronized so that the consumer doesn't try to consume an item that hasn't yet been produced. Synchronization will be discussed in great details in chapter 6 and 7. We just introduced the shared memory model. Let's take a look at a message passing model. Message passing provides a mechanism to allow processes to communicate and to synchronize their actions without sharing the same address space. It is particularly useful in a distributed environment where the communication process may reside on different computers connected by a network. A message passing facility provides at least 2 operations: send message and receive message. If process P and Q want to communicate, they must send messages to and receive messages from each other. A communication link must exist between them. We must consider the following questions. How are links established? Can a link be associated with more than 2 processes? How many links can there be between every pair of a communicating process? What is the capacity of a link? Is the size of a message that the link can accommodate fixed or variable? Is a link unidirectional or bidirectional? Chapter 19 covers the physical part of the link, such as a shared memory, hardware bus, and a network. In here, we're going to discuss the logically implement a link. So we'll think about direct or indirect communication, synchronized or asynchronized communication, automatic or explicit buffering. Under direct communication, each process that wants to communicate must explicitly name the recipient or sender of the communication. In this scheme, the send and the receive primitives are defined as follows. Send P, the message. So send a message to process P. Receive Q message. Receive a message from process Q. A communication link in the scheme has the following properties. Links are established automatically. A link is associated with exactly one pair of communicating process. Between each pair, there exists exactly one link. The link may be unidirectional, but it is usually bidirectional. With indirect communication, the messages are sent to and received from mailboxes or ports. A mailbox can be viewed abstractly as an object into which messages can be placed by process and from which message can be removed. Each mailbox has a unique identification. For example, POSIX message queues use an integer value to identify a mailbox. A process can communicate with another process via a number of different mailboxes, but two processes can communicate only if they have a shared mailbox. In an indirect communication, a communication link has the following property. The link established only if processes share a common mailbox. A link may be associated with many processes. Each pair of processes may share several communication links, and links may be unidirectional or bidirectional. In indirect communication, a new mailbox or port is created. Then the processes send and receive messages through mailbox. When the communication ends, the mailbox is deleted. So we have the following. The send A message sends a message to mailbox A. Receive A message, receive a box from mailbox A. Now suppose that process P1, P2, and P3 all share mailbox A. Process P1 sends a message to A, while both P2 and P3 execute a receive from A. So which process will receive the message sent by P1? The answer depends on which of the following methods we choose. Allow a link to be associated with at most two processes. Only allow one process at a time to execute a receive operation. Allow the system to select arbitrarily which process will receive the message. Either P2 or P3, but not both, will receive the message. The system may define an algorithm for selecting which process will receive the message. For example, round robin, where processes take turns receive the message. The system might identify the receiver to the sender. Communication between processes take place through calls to send and receive. There are different design options for implementing them. Message passing may be either blocking or non-blocking, known as synchronized and asynchronized. Blocking is considered synchronized, so blocking send, the sender is blocked until the message is received. Blocking receive, the receiver is blocked until a message is available. Non-blocking is considered asynchronized. Non-blocking send, the sender sends the message and continue. Non-blocking receive, the receiver receives either a valid message or a no message. Different combinations of send and receive are possible when both send and receive are blocking we have a rendezvous between the sender and the receiver. In this producer-consumer message passing, we use blocking, send, and the receiving statements. The producer only invokes the blocking send call and waits until the message is delivered to either the receiver or the mailbox. Likewise, when the consumer invokes receive, it blocks until a message is available. Whether communication is direct or indirect, messages exchanged by communicating processes reside in a temporary queues. Basically, such queues can be implemented in three ways. Zero capacity. So in this way, no message are queued. The sender must wait for receiver. So it is a rendezvous between the sender and the receiver. Bounded capacity. The length of the message is finite. If the link is full, the sender must wait. Unbounded capacity. The queue's length is potentially infinite. Thus, any number of messages can wait in it. The sender never blocks. Several IPC mechanisms are available for POSIX systems, including shared memory and message passing. Here we explore the POSIX API for shared memory. POSIX shared memory is organized using memory mapped files, which associate the region of shared memory with a file. A process must first create a shared memory object using sh3 system call. So here we have fd equal sh3 the name specifies the name of the shared memory object. Processes that wish to access this shared memory must refer to the object by this name. O_create, that means we are going to create this shared memory. Then vertical bar, then O_RDWR, that means the object is open for reading and writing. The last parameter 0666 establishes the file access permissions of the shared memory object. So if this sh3_open, if it is successful, it will return an integer file descriptor for the shared memory object. Once the object is established, the ftruncate function is used to configure the size of the object in bytes. So ftruncate, the first parameter, is this file descriptor returned by the sh3_open, so fd. Then the second parameter, 4096, that is set the size of the object to 4096 bytes. Finally, the mmap function establishes a memory mapped file containing the shared memory object. It also returns a pointer to the memory mapped file that is used for accessing the shared memory object. Let's take a look at programs use the producer-consumer model in implementing shared memory in POSIX system. On the left side, the program is for producer. On the right side, the program is for consumer. Let's first take a look at the program on the left side, which is the producer. The producer established a shared memory object and writes to shared memory. First, we have a constant integer size, which is 4096. It will be served as a bytes of the shared memory object. Then we have the name. Because this is a C program, so we have a constant character, and we have a pointer, name, and we give OS. So OS will be the name for the shared memory object. Then we have constant character. Message 0 is hello, message 1 is word. Then we have integer sh_m_fd, that's the file descriptor. Then we have a pointer. The pointer will be point to shared memory object. Then we call the shm_open system call. And this call, if it is successful, it will return. And so we assign the file descriptor, which is integer, to shm_fd. So in this shm.open system call, we pass in name. The name is OS. And then we say create and read write, and then the file permission. Then we set this memory size by f_truncate system call. So we pass in the file descriptor, which is shm_fd, and the size. The size is constant, is 4096 we declared at the beginning. Then we use mmap functions. Mmap function returns a pointer to the memory mapped file that is used for accessing the shared memory object. So it will return a pointer and will be assigned to PTR. Because PTR we declared as a pointer. So let's take a look at the function mmap. So we pass in parameters 0, size, priority write, because it's a producer program. Map shared. The parameter map shared is a flag specified that changes to shared memory object will be visible to all processes sharing the object. Then we call the sprintf function to write the formatted string to the pointer PTR. So sprintf, there's a %s, that means a format is a string. We're going to write a string to PTR. After we write message _0, which is hello, that's a 5 characters, right? We need to update the PTR. So PTR plus equal the string length of message _0. Then it will pointing to the next available position in the shared memory. The PTR will be pointing to the next position after O. Sprintf PTR, then we print the message _1, which is word, and we also need to update PTR. After message 1 is written in the memory, the PTR will be pointing the next position after the last character, which is an exclamation symbol. Let's take a look at a consumer process. It shows on the right side. The consumer reads and outputs the contents of the shared memory. First is also declare the size, the name, the integer shm_fd, the file port descriptor. Then we also have a pointer. Then it called the system call shm.open, and the name and the o_read only. So it's only read from the memory. It cannot write because it's a consumer. Then this program didn't have f_truncate because the consumer just read, right? It doesn't write, so it doesn't need to create the memory, the size of the memory. Then it also called the mmap function. So in mmap, its priority just read, right? In the producer, its priority is write, but in the consumer, it's read. Then printf, so it read from the shared memory object. Then the consumer called the function shm_unlink. So it will remove the shared memory segment after the consumer has accessed it. Previously, we discussed the shared memory passing in POSIX system. Let's take a look of message passing in Mac operating system. Mark was especially designed for the distributed systems, but was shown to be suitable for desktop and the mobile system as well. Most communication in Mark, including all inter-task communication, is carried out by messages. Messages are sent to and received from mailboxes, which are also called ports in Mark. Ports are finite in size and unidirectional. For two-way communication, a message is sent to one port and the response is sent to a separate reply port. Each port may have multiple senders but only one receiver, just like a mailbox in your home. All other people can send you mails, but you only have just one receiver, that's you. Associated with each port is a collection of port rights. Mark port right receive is to receive a message from a port. Mark port right send is to send a message to a port. Messages are sent and received using the mark_MSG function. The ports are created using the function mark_ports_allocate function. The send and the receive operations themselves are flexible. For example, when a message is sent to a port, its queue may be full. If the queue is not full, the message is copied to the queue and the sending task continues. If the port's queue is full, the sender has several options. It can wait indefinitely, or wait at a limited time, n milliseconds, or it doesn't wait at all, but rather return immediately, or it just temporarily caches a message. A message is given to the operating system to keep. Let's take a look of a program where it shows the client task constructing a header and sending a message to the server, as well as the server task receiving the message sent from the client. At the beginning, the program includes mark.h, the library file. Then second, it declares a message, mark message. A mark message contains two fields. The first field is the fixed size message header containing metadata about the message, including the size of the message, as well as the source and the destination parts. The second field containing the data. mark_port_t client. So we used the API to create a port for the client. The name is client. Then we also create the server port. This part of code is for the client code. First, struct message. So we have a variable called message, and the type is a mark message. Then we constructed the header. So we specify the size. Remote port is the destination. That's a server. And the local port is the source. That's from client. So the client is going to send a message to the server. Now the code called mark_message. In mark_msg, the first parameter we pass in the header of the message. Then we specify the second parameter mark_send_message. So this function is going to send a message. Then we pass the size of the message in the other parameter, because here we're going to send a message. So mark_port_no, that's the name of the receive port, which is unnecessary, right? Because we are going to send a message, not receiving a message. This part is server code. It also creates a message in mark message type. Then it calls mark_msg function. The second parameter is a mark_rcv_msg. So it's going to receive a message. The fifth parameter, the name of receive port, and this time you need to put the server because that's the name of receive port. Windows provides support for multiple operating environments or subsystems. Application programs communicate with this subsystem by message passing mechanism. Thus, application programs can be considered clients of a subsystem server. The message passing facilities in Windows is called Advanced Local Procedure Call, ALPC facility. It is used for communication between two processes on the same machine. Server process publish connection port objects that are visible to all processes. When a client wants services from a subsystem, it opens a handle to the server's connection port object and sends a connection request to that port. The server then creates a channel and returns a handle to the client. The channel consists of a pair of private communication ports, one for client-server messages, the other for server-client messages. Additionally, communication channels support a callback mechanism that allows the client and server to accept requests when they would normally be expecting a reply. ALPC facility in Windows is not part of Windows API. Hence, it is not visible to the application programmer. Rather, applications using the Windows API invoke standard remote procedure call, RPC. When the RPC is being invoked on a process on the same system, the RPC is handled indirectly through an ALPC procedure call. Additionally, many kernel services use ALPC to communicate with client process. A pipe is a technique used for inter-process communication. A pipe is a mechanism by which the output of one process is directed into the input of another process. Thus, it provides one-way flow of data between two related processes. We will explore two common types of pipes used on both Unix and Windows systems, ordinary pipes and named pipes. Ordinary pipes allow two processes to communicate in standard producer-consumer fashion. The producer writes to one end of the pipes, the write end, and the consumer reads from the other end, the read end. As a result, ordinary pipes are unidirectional, allowing only one-way communication. If two-way communication is required, two pipes must be used, with each pipe sending data in different direction. In ordinary pipes, a parent process creates a pipe and uses it to communicate with a child process that it creates. We also have a named pipe. It can be accessed without a parent-child relationship. An ordinary pipe cannot be accessed from outside the process that created it. Typically, a parent process creates a pipe and uses it to communicate with a child process that it creates by fork function. Recall from previous section, a child process inherits open files from its parent. Since a pipe is a special type of file, the child inherits the pipe from its parent process. This figure illustrates the relationship of the file descriptors in the FD array to the parent and the child process. So FD0 means read end, FD1 is write end. As this figure illustrates, any writes by the parent to its right end of pipe FD1 can be read from the child from its read end FD0 of the pipe. Ordinary pipes on Windows system are termed anonymous pipes, and they behave similar to their Unix counterparts. They are unidirectional and they employ parent-child relationship between the communication process. Named pipe is an extension to the ordinary pipe concept on Unix. A traditional pipe is unnamed and it lasts only as long as the process. A named pipe, however, can last as long as the system is up, beyond the life of the process. It can be deleted if no longer used, so it's more powerful than ordinary pipes. In named pipes, communication is bidirectional. No parent-child relationship is necessary between the communicating process. Several processes can use the named pipe for communication. It's provided on both Unix and the Windows system. Usually, a named pipe appears as a file and generates processes attached to it for inter-process communication. A FIFO, first in, first out file, is a special kind of file on the local storage which allows two or more processes to communicate with each other by reading/writing to or from this file. A FIFO special file is entered into the file system by calling mkmfifo, so make FIFO function in C. Once we have created a FIFO special file in this way, any process can open it for reading and writing in the same way as an ordinary file. However, it has to be opened at both ends simultaneously before you can proceed to do any input or output operations on it. In previous sections, we described how processes can communicate using shared memory and message passing. These techniques can be used for communication in client-server systems as well. In this section, we explore two other strategies for communicating in client-server system, socket and the remote procedure calls, RPC. A socket connecting to the network is created at each end of the communication. Each socket has a specific address. This address is composed of an IP address and a port number. Sockets are generally employed in client-server applications. A pair of processes communicating over a network employs a pair of sockets, one for each process. A socket is identified by an IP address concatenated with a port number. For example, the socket 161.25.19.a, then colon 1625. So the first part before the colon is the IP address of the host. The second part after colon 1625 refers to the port. All ports below 1024 are considered well-known and are used to implement standard service. For example, port for SSH is 22. Port for FTP is 21. For the web and the HTTP, it listens to port 80. The IP address 127.0.0.1 is a special IP address known as the loopback. When a computer refers to IP address 127.0.0.1, it is referring to itself. This mechanism allows a client and server on the same host to communicate using the TCP/IP protocol. The IP address 127.0.0.1 could be replaced with the IP address of another host running in addition to an IP address. An actual host name, such as www.join.edu, can be used as well. In this example, host X, its IP address is 146.86.5.20. It is assigned by the port 1625. So the socket is the IP colon the port number. And for the web server, we know the web server is listening on port 80. And its IP is 161.25.19 and A. So the socket is 161.25.19A colon 80. So the connection will consist of a pair of sockets on host X and on the web server. The packets traveling between the hosts are delivered to the appropriate process based on the destination port number. All connections must be unique. Therefore, if another process also on host X wishes to establish another connection with the same web server, it will be assigned a port number greater than 1024 and not equal to 1625. This ensures that all connections consist of a unique pair of sockets. Java provides 3 different types of sockets. The first one is a connection-oriented TCP sockets. I implemented with the socket class. The second one is connectionless UDP sockets. Use the datagram socket class. Finally, the multicast socket class is a subclass of the datagram socket class. A multicast socket allows data to be sent to multiple recipients. In this example, the Java program describes a date server that uses connection-oriented TCP sockets. The operation allows clients to request the current date and time from the server. The server listens to port 6013. You can specify other ports as long as it is greater than 1024. When a connection is received, the server returns the date and the time to the client. The server creates a server socket object that specifies that it will listen to port 6013. The server then begins listening to the port with the accept method. The server blocks on the accept method, waiting for a client to request a connection. When a connection request is received, accept function returns a socket that the server can use to communicate with the client. So here we define the variable name as a client. So when the client requests, the accept function will return the request and will be assigned to the client variable. Then server will communicate with the client. The server first established a print write object that will use to communicate with the client. The name of the print writer is pout. Then pout call the print line function and write the date. The socket will send this date to client. Once the server has written the date to the socket, the server closes the socket to the client and resumes listening for more requests. This Java program implements the client. A client communicates with the server by creating a socket and connecting to the port on which the server is listening. So in this code, the client creates a socket and requests a connection with the server at IP address 127.0.0.1 on port 6013. Once the connection is made, the client can read from the socket using normal stream I/O statements. After it has received the date from the server, the client closes the socket and exits. As we mentioned earlier, the IP address 127.0.0.1 is a special purpose IP address and is called the local host or loopback address. All computers use this address as their own. It is referring to itself so it allows a client and server on the same host to communicate using the TCP/IP protocol. In distributed computing, a remote procedure call, RPC, is when a computer program causes a procedure or subroutine to execute in a different address space, commonly on another computer on a shared network, which is coded as if it were a formal or local procedure call, without the programmer explicitly coding the details for the remote interaction. That is, the programmer writes essentially the same code whether the subroutine is local to the executing program or remote. This is a form of client-server interaction. The RPC allows a client to invoke a procedure on a remote host as it would invoke a procedure locally. The RPC system hides the details that allow communication to take place by providing a stub on the client side. Typically, a separate stub exists for each separate remote procedure. When the client invokes a remote procedure, the RPC system calls the appropriate stub, passing it the parameters provided to the remote procedure. This stub locates the port on the server and measures the parameters. The stub then transmits a message to the server using message passing. A similar stub on the server side receives this message and invokes the procedure on the server. If necessary, return values are passed back to the client using the same technique. On Windows system, stub code is compiled from a specification written in the Microsoft Interface Definition Language, MIDL, which is used for defining the interface between client and server programs. In parameter marshalling, there may be problems because two systems, they may have different formats. Some systems, known as a big endian, store the most significant byte first, while other systems, known as a little endian, store the least significant byte first. So neither order is better. So rather the choice is arbitrary within a computer architecture. To resolve differences like this, many RPC systems define a machine-independent representation of data. One such representation is known as external data representation, XDR. On the client side, parameter marshalling involves converting the machine-independent data into XDR before they are sent to the server. On the server side, the XDR data are unmarshaled and converted to the machine-dependent representation for the server. How does the client know the port numbers on the server? There are two approaches. The first approach is a fixed port number. The binding information may be predetermined in the form of fixed port address. At the compile time, an RPC call has a fixed port number associated with it. Once a program is compiled, the server cannot change the port number of the requested service. The second approach is dynamic. Binding can be done dynamically by a rendezvous mechanism. Typically, an operating system provides a rendezvous, also called matchmaker daemon, on a fixed RPC port. This figure shows a sample interaction. A client sends a message containing the name of the RPC to the rendezvous daemon, requesting the port address of the RPC it needs to execute. The port number is returned. Then the RPC calls can be sent to that port until the process terminates or the server crashes. This method requires the extra overhead of the initial request but is more flexible than the first approach in which the port number is fixed. Although RPC are typically associated with client-server computing in a distributed system, they can also be used as a form of IPC between processes running on the same system. The Android operating system has a rich set of IPC mechanisms contained in its binder framework, including RPCs that allow one process to request services from another process. Android defines an application component as a basic building block that provides utility to an Android application, and an app may combine multiple application components to provide functionality to an app. One such application component is a service, which has no user interface but instead runs in the background while executing long-run operations or performing work for a remote process. Here the brief description between a service and its clients is set up. The clients of the service on the local side would implement on-service connected function call and on-service disconnected method, so they can be notified when a successful connection to the remote service is established and when it goes away. They would then call bind service to set up the connection. The service onBind method will be implemented to either accept or reject the connection, depending on the intent it receive. The intent passed to the bind service function call. If the connection is accepted, it returns an instance of the stub subclass. If the service accepts the connection, Android calls the client onService connected method and passes it an iBinder object, a proxy for the stub subclass managed by the service. Through the proxy, the client can make calls on the remote service.